Welcome to This Explainer. Today, we're diving into the hidden physics of your daily commute and everyday activities. You know, absolutely everything in nature is in motion, from massive astronomical objects spinning in space to things we barely even notice, like a flitting butterfly, gathering clouds, or just a car driving down a straight highway. So we're going to explore the mathematical rules that actually govern all this movement. We'll be looking closely at linear motion, which is basically just motion in a straight line, and how really understanding it could literally save your life.
Okay, picture this. It's a highly relatable, yet potentially dangerous scenario. You're driving down the highway right behind a massive truck. Suddenly, you've got to ask yourself a very practical question. How much distance do you actually need to maintain from that truck to avoid a collision if it just slams on the brakes? And, more importantly, does that safe following distance depend on the speed you're currently going?
But before we can safely answer that highway dilemma, we have to unpack a few fundamental concepts about motion that scientists have been calculating for centuries. We need to look at how we describe motion, not just with words, but with numbers and equations. Specifically, we've got to break down the differences between speed, velocity, and acceleration.
Part 1. The ancient roots of speed.
Now, the idea of mathematically calculating speed, it actually dates all the way back to ancient Indian texts like the 5th century Aryabhatiya. The concept that an object's speed is just distance traveled divided by time taken is incredibly well established. It's definitely not a modern invention just for cars and trains. To see how they apply this back then, check out this brilliant math problem from the 14th century Ganita Kaumudi. It sets up a puzzle about two postmen walking toward each other. The total distance between them is 210 yojanas, an ancient unit of distance. Postman 1 travels at a speed of 9 yojanas per day, while Postman 2 covers 5 yojanas per day. So in how many days will they meet?
This brilliantly illustrates early speed calculations. If you just add their speeds together, you find they cover a combined distance of 14 yojanas per day. Divide the total 210 yojanas by that combined daily speed, and boom, they meet in exactly 15 days. Over that time, the first postman covers 135 yojanas, and the second covers 75.
Moving on to part 2, speed versus velocity.
Let's pull this into a more modern context. Speed is great for telling us how fast something is moving, like our postmen, but it tells us absolutely nothing about the direction. And in the real world, you usually need direction to get the full picture. This is where displacement comes in. Displacement measures the net change in an object's position. To describe it perfectly, you need a numerical value, its magnitude, and a specific direction. Displacement only cares about where you started and where you ended up. It completely ignores whatever winding path you took to get there.
To see this in action, imagine an athlete, let's call him Sarang, swimming in a pool. He swims 25 meters from one end to the other, and then 25 meters straight back to his starting point, taking 50 seconds in total. His total distance traveled is 50 meters, sure, but because his starting position and stopping position are literally exactly the same, his net displacement is 0 meters.
So how does this impact velocity? Well, average velocity is calculated by taking displacement and dividing it by time. Since Sarang's displacement for the entire swim is 0, his average velocity for the whole swim is exactly 0. Yep, even though his average speed was a steady 1 meter per second. Velocity demands an actual change in position over time.
All right, part 3, understanding acceleration. Now that we know velocity is a package deal of speed and direction, what happens when velocity changes? That's acceleration. Acceleration measures how fast your velocity is shifting, whether you're speeding up, slowing down, or changing direction. Imagine a bus on a straight highway. Let's say it's cruising at an initial velocity of 36 kilometers per hour. Then, the driver hits the gas for exactly 10 seconds, pushing the bus up to 54 kilometers per hour.
Let's break down the math real quick. First, we convert those speeds into meters per second for standard physics. 36 kilometers per hour is 10 meters per second. 54 kilometers per hour is 15 meters per second. Take the final velocity, subtract the initial, and we get a change of 5 meters per second. Divide that by our 10-second interval, and we end up with an average acceleration of a positive 0.5 meters per second squared. Because it's speeding up, this acceleration acts in the exact same direction the bus is moving. But hey, what speeds up must slow down, right? Say that same driver spots an obstacle on the road. They slam on the brakes. The bus drops from 15 meters per second to a complete dead stop, 0 meters per second, in just 5 seconds.
This rapid drop results in a negative acceleration of -3 meters per second squared. You just take the final velocity of 0, subtract the initial 15, and divide by 5 seconds. That minus sign, absolutely crucial. It tells us the acceleration is acting completely opposite to the bus's forward motion.
Which brings up a really fascinating question that trips people up all the time. Think about this. Can an object be moving incredibly fast but have absolutely zero acceleration?
The answer is a massive yes. Since acceleration specifically measures the rate of change in velocity, a car cruising at a perfectly constant, steady speed on a flat highway, even if it's going 100 kilometers per hour, has zero acceleration. It really doesn't matter how fast you're going. If your velocity isn't changing, your acceleration is zero.
Finally, Part 4, the physics of braking.
Let's bring this all the way back to that highway scenario behind the truck. When you slam on the brakes, your car still moves a certain distance before fully stopping. That stopping distance is dictated by a few critical things: your initial velocity, right when you hit the pedal, the road conditions, the maximum negative acceleration your brakes can actually generate, and of course, your own physical reaction time before your foot even touches the brake.
So to answer our very first question, yes, the safe distance you have to maintain behind a vehicle absolutely depends on your speed. Higher initial velocities require significantly more distance to safely stop simply because that negative acceleration needs way more time and space to bring your velocity down to zero. So I'm going to leave you with this to chew on. Next time you're out on the highway trailing a large truck, look down at your speedometer. Ask yourself, based on the undeniable physics of your current velocity, your car's braking limits, and your own reaction time, are you truly leaving enough space to safely stop? Because understanding the physics of everyday motion isn't just about passing a test, it's about navigating the real world safely. Thanks for joining me on this explainer, and keep questioning the science all around you.